Swayam Prabha. Digital India. Educated India.
Let us continue with what we had been doing so far, that we have shown that if we do a multi-stage expansion of work, then I can get more work out of the system. That means that if I continue it, that if I now carry out the process of expansion from an initial state V1 to V2 in multiple stages, then the idea is this: under what condition I can get a maximum amount of work? That is the question. So that process can be started in this way, that the work of expansion. So again, we come back to the work of expansion in multiple stages. So we come back to that PV diagram for the gas, when temperature is kept constant, temperature is kept constant, and we have the equilibrium curve for the pressure volume of a gas, and I want an expansion of the gas from the volume V1 to volume V2. So this is my P2 and this is my P1. Equilibrium pressure of the gas is P1 corresponding to the volume V1, equilibrium pressure of the gas P2 correspondingly to the volume V2. Now, if I want this process to be carried out in a multiple stages, and let us see how can we do it. Say if I go from V1 to V prime in the first stage, so I have an opposing pressure corresponding to this P opposing. This is the opposing pressure. Then I want an expansion from V1 to V prime. So V prime is my final volume, V1 my initial volume. This is a small change in volume, V prime minus V1, and against a pressure that I have chosen to be P opposing, which is less than P1, which is P1 is the equilibrium pressure corresponding to this volume V1, but I have chosen a pressure which is less than V1. So I allow the gas to expand against a pressure P opposing this one, and this is my small work W for this case, and this is the shaded area that you can see. Now, if I look at this P opposing, what is this P opposing? P opposing, I have chosen a point deliberately on this particular equilibrium curve, P equilibrium. So P equilibrium basically is P1 minus some small change, P1 minus some delta P. Delta P is this change. So basically P opposing P1 minus delta P is this one. So this is V prime minus V1, and that is a change in volume. and that is, I can write it as this. If it is small, then V prime minus V1 is basically a small quantity. Then I write it as P1 minus delta P times delta V. Small change, I call this small change as some delta V, the standard notation, the small change in volume. So P1 minus delta V. Now there are two terms that you can see, that is P1 delta V delta. For this one, since I started from V1, I write it say delta V1, and that is delta V1, this is delta V1 for the sake of simplicity. It is delta P times delta V1. Now this is a quantity which is order of magnitude lower than this quantity. It is a simple pressure times the change in volume. This is a change in pressure and change in volume. This is a quantity which is much smaller compared to this one. So what I can do, I can neglect it in this case, and we write it as P1 delta V1, and that is my W for the first stage. So W for the first stage. So if I carry out exactly the same process for the next stage, say for another P1 prime, P opposing prime, and proceed exactly in the same way up to V2, then I carry out the same change, same process repeated number of cases. Then for each step I call it Wi, I call it Pi times delta Vi. Then I make a sum over all these steps Pi. Then this will be my total work done for expansion, that is Pi times V delta V1. Now the most characteristic thing is this, that I have chosen this P opposing to again a pressure which is basically the equilibrium pressure. So this P1 is this is P1 times the delta V1. Basically P1 times the delta V1 change. Next times another P times that P again is a point corresponding to corresponds to a equilibrium point on this curve. So for each P is an equilibrium point. So each Pi are all equilibrium pressure for the gas. That means inside and outside always I keep it same. So the surrounding remains the same, but the system changes slowly as it proceeds, as we go from V1 to V2. So if I carry out this process and repeat it infinitely, so infinite repetition, infinitely repeated means I discretize each step in such a way that delta V is very small and smaller and smaller and smaller. So that means I have the summation, instead of a summation, I can make an integration over P times, I call dV. So delta V, I go over to dV and Pi. So for infinitesimal process, P goes to P and delta V, I write it as dV, and this is basically an integral over P times dV into V2, from V1 to V2. So I am going from initial to final state, and each stage I have a pressure. I have kept the gas outside and inside pressure I have kept almost the same. Infinitesimally I am trying to reduce the pressure at each step by an infinitesimal amount, so that the outside pressure and inside pressure remain same, so that there an equilibrium condition is maintained throughout. So this is a very stringent condition on the system, and that gives you a W. That W is basically P times the dV, and that process is called a reversible process. We call this infinitesimally repeated process infinitesimally divided process, and this is called a reversible process, in which the change I have this change in this pressure times the volume, the pressure times the delta dV, this corresponds to a pressure corresponds to an equilibrium pressure corresponds to an equilibrium pressure that I have mentioned, and that gives me the work, that is integral V1 to V2 gives the work W, and if I know how P varies with V, that is given by this curve itself, how P varies with V. So if I write this to for a specific case, so this is the general formula, this is a perfect general result, but specialized case for ideal gas. For ideal gas, I have an equilibrium pressure P equal to, that is nRT, where R is the universal gas constant, T is the temperature, N is the number of moles divided by this volume. This is an universal formula. So for ideal gas, there is an universality. So for this special case, you can replace this P and work it out explicitly for n mole of a gas. So what I do, I change the volume V1 to V2 for an ideal gas, and I have nRT by volume V times dV. So I know how this P changes with V according to this curve all throughout, and this is replaced by nRT by V, and it is auto, since temperature is always constant, you have nRT times 1 by V dV V1 to V2, and that is equal to nRT ln log of volume V2 by V1. So this is a very stringent condition that I have always maintained in changing the state of the gas or the volume of the gas from the volume V1 to V2, keeping temperature always constant. And in the process, what I have done, I have reduced the pressure of the gas by infinite amount at each stage of for compressing, for expanding the gas from V1 to V2. For each stage, I am lifting a weight on the piston by an infinitesimal amount, and the process is called the reversible process. So this is a reversible path, and this gives me a typical expression. But for any general gas or real gas, which is not an ideal thing, ideal gas, I cannot write down explicitly this expression, but this is the most general expression for any gas that we can imagine. For a real gas, you will have to replace this by another pressure and pressure volume relations. So that those are the questions of details that we need not work at this moment. And but this tells us that from a multi-stage process, I can visualize and think of a situation where I can keep the change of state of a system. The change of state of the system is most important. I can do it on it by keeping the equilibrium condition between the system and the surround all throughout. So that is sometimes called a quasi-static process. So this quasi-static process is basically the reversible process, and the details is that the surrounding does not change. System changes from volume V1 to V2 at a constant temperature, but the system, while the system gets changed, the surrounding does not change at all. So surrounding while the system is changed in a reversible way, but the surrounding does not change. So that is the crucial thing that should be kept in mind while I am discussing the reversible process. So all finite process where I am not maintaining this kind of a stringent condition, that is I am not keeping the infinitesimal small changes and do a finite change, then they are called or irreversible process. So irreversible process is something that we normally do for any finite change. So if I make an expansion of a gas from volume V1 to V2, say 1 or 2 stages, they are called basically the irreversible stages, irreversible process of expansion. But if I carry out the same process by an infinitesimal divisive processes, and each stage I can maintain the equilibrium condition, that process is the reversible process. That is something about this reversible and irreversible changes. They are crucial for thermodynamics because that any change of state that is carried out reversibly can be accounted for by the methods of calculation of thermodynamics, that as we will proceed you will see. But for irreversible process we will see often that there are difficulties because of the appearance of some inequalities and other things that when we will see, we'll see those things as we proceed further. But before just conclusion, let me proceed also for the next another process that is called a cyclic process, because cyclic processes are important, as we see that I go from a stage A to stage B. That is, if I go for an expansion from a volume V1 to V2 and come back again through by another means to from V2 to V1, I have completed a reversible process, completed a complete cycle. So a cyclic process is something, cyclic process, suppose I consider a gas, again we start with the PV diagram, and then what I do, again I make an expansion from the volume V1 to V2. Again, this is my pressure P1, this is my equilibrium pressure P2. Then what I do, I make an expansion of the gas from volume V1 to V2 by keeping a pressure which is much low, say at this pressure P2. So first stage I carry out an expansion and then I will compress the gas back to V1. So for the process V1 to V2 expansion of the gas, I choose my pressure P2. So work of work of expansion here from V1 to V2, and I choose my pressure to be P2, that is the final pressure corresponding to V2, then I have V1 to V2, so it is V2 minus V1. So this is a work of expansion, and the area is basically the P2 times the V1 to V2, that is a work of expansion. Then if I revert back, then I come back from V2 to V1, that is a work of compression. So for work of compression, I can choose my pressure, say high pressure, so the gas can be compressed. Once I have gone to this volume expansion, then I choose a pressure P1. So this is the work of compression is basically I go P1 from this, I go from V2 to V1. So final stage is V1 minus V2. So this is my work of compression. So for the total process, for the cyclic process, or for the entire cyclic process, what we see that, or you can write W cycle equal to basically the summation of the two, that is P2 V2 minus V1 times plus P1 into V1 minus V2. That is basically P2 minus, so if I write it as V1 minus V2 minus V1, V2 minus V1, then P2 minus P1 times V2 minus V1. This is positive quantity. V2 minus V1 is a positive quantity, but P2 minus P1 is a negative quantity. Then I see that in the cyclic process, ultimately no work is obtained from the system. We don't get any work from the system expansion, or compression. We have lost some work in the process, and a finite process. This is an irreversible process, irreversible cyclic expansion. So although kept at a constant temperature, T equal to constant process. So T constant process, and this is always a negative quantity that you can see. Now you can see that this is, you can also see that why it is negative, that if you calculate that, if you see the each term, that is the this one and this one, this is this one and this one. So if it is subtracted from the something is larger part is subtracted from this one, then you get this negative quantity. So that is the cyclic process for, this is for the irreversible cyclic process. So for the irreversible cyclic process, we see that the system has returned to the initial state. That means the system, the total internal energy has not changed anywhere, anything. So system remains the same, remains in the same position. So the initial characteristics we have recovered, but in the entire process, the system has not done anything more than else, that you will have to do, you have done more work on the system. That's why W cycle is ultimately negative. But if I carry out the same process reversibly, so work out the process for a reversible cyclic process. For a reversible cyclic process, what happens? That you do not actually carry out the expansion and compression in this way. What you do, you do the same change of state from volume V1 to V2 and return. That is, you go from V1 to V2 and then come back from V2 to V1, and in this way you get a complete cyclic process, and W cycle will be exactly the same thing that as we derived here, that is P times dV. So it is basically all throughout the process, if I change the state from V1 to V2, that is P1, this is P2. So all throughout the process, I have got a curve like this. So this is an area under the curve, and this is basically V1 to V2 P times dV plus V2 to V1 P times dV. And you see that P times the dV and P times dV, and this is the integral limits can be changed with a minus sign, and you will get simply 0. That I can change it and I get it to be 0, because V1 to V2 P dV, I can write as a minus of V1 to V2, because I am actually reverse the sign, reverse the limits of integration, and over dV, and that is basically is equal to 0. Therefore, for W cyclic, for the reversible process, the work done by the system is 0. That is, no work has been lost in the process, but no loss, no gain, that the total work done is 0. But here you see, for the irreversible process, for the irreversible cyclic process, under isothermal condition, the work done over an entire cycle is a negative quantity. There is no positive work you can have on the system. So that is not an always a fruitful process. A good process would be to carry out a process reversibly or under quasi-static condition. That means I am changing the volume from V1 to V2, maintaining each stage the pressure at an equilibrium condition. So I lift the pressure slightly from pressure P1 to slightly lower it to get another new pressure, and again lift a small amount of pressure out of it, and each stage there is an expansion, and if this is repeated infinitely, then I have a process which is basically there is no loss in the system. That is, the total work done over a cycle is 0. Here this is negative quantity. So the process, what we want to emphasize is that the work process is something that depends on the way we carry out the work of expansion or work of compression. And for keeping a cyclic process either under reversibly or under reversible condition, all these processes can be carried out in infinitely different ways. And choice is yours, that how work can be profitably obtained by allowing the system to work under certain conditions. So that would be the major goal that we'll do next time. But before that, I need to emphasize certain things. I have made some reference to small quantities like V prime minus V1 is the change. I am writing delta V. Sometimes delta V is changed over to dV. So these are the things. These are small quantities. Sometimes they are called differentials or small changes. So small changes in temperature, small changes in work, small changes in pressure. The different quantities have small changes. So whether these small changes can be related to some mathematically stringent terms, some relatively stronger terms, that whether they can be small quantities can be treated as differentials, and under what condition they can be any small quantity can be treated as a differential of a function. So, I will talk about that thing, because we have seen that for reversible condition I need to have a differential dV when p is a function of a some volume. So, differential of a function is an important quantity. So, I will try to discuss something about this differentials, whether they are exact or inexact, and try to clarify those things in my next lecture. So, with this I thank you all for your attention.